Now that we have a intuition about what dimension reduction is, we're going to go ahead and apply that to our clustering output that we had. So I'm going to make a new section. I'm going to call this dimension reduction. And so the first thing I'm going to do is I want to first scale I want to scale or standardize our data. So to do that, I'm going to call scikit-learn, and then I'm going to call pre-processing. Then I'm going to input min max scalar. I'm going to set our df ready is going to equal our Canaan model output minus while dropping those special columns that we had. So we want to drop assigned cluster because we don't want that to get in the way of figuring out dimensions. We also want to get species. We don't want that to get in the way, and then names is just extra data. And then I want to go ahead, I'm going to set a little x matrix, and I'm going to set that equal to our min max. I'm going to use our min max scalar, and I'm going to fit our df ready transformation. And then I'll run that. Let me get species. Here we go. And now our data is standardized. And let me run you through really quickly what this is doing with the data. I'm going to go back to our Excel example. So why we need to standardize the data is because we are looking for the variance in the data. And when you have a column like this with big numbers, and then a column like this with little numbers, if we just run this through the algorithm, we'll see that the difference between, say, this, like, this and this right here is almost like 300, about 300 in difference, which is huge compared to this, which is only one in difference. So what this picks up as is huge variance, and this picks up as almost no variance at all, which is not good for what we want to do. So what a scaling algorithm does is let me delete this. It will go ahead and it will standardize the data so we can compare it. In this case, we are using a min-max method. And the way that min-max works is what we'll do is we are going to take whatever the value is and then subtract it from the minimum value of the data. And let me just make sure I get my stickies right here. And then we are going to divide that by the difference between the min value, which I'll just copy this and paste it again. The difference between the min value and the max value. And then if we can go ahead and run that on the different columns. And you see then we are able to better capture the variance that we have. And it looks like I got the stickies wrong on this. Let me redo that to make sure I want it on the numbers, not on the letters. That was my mistake. Okay. That should look a lot better now. And so now, we now have a matrix where we have the variance of data to be a lot more comparable than what we had before. We can see easily right here that this is the smallest value, while this is the largest value. Um, and then we can notice that in this case, bed increased by 0.3, or bath relatively increased by 0.3, but bed is only 0.25. You can see this, that basically it looks like the square feet and the bedroom are both going up by 0.3, but the variance is 0.25, where the variance here is 0.3. So it just puts everything on a scale that you can almost think of these as like percentiles. This is in the 100th percentile of being the biggest, of having the most bedrooms. This is in the 0th percentile. These are on the 33rd percentile. These are in the 25th percentile. This is in the 50th percentile, and so forth. But that is what standardization is doing, so we can better capture the variance of our data set once we throw it into um, our dimension reduction algorithm. And so for this case, now that we have that ready, I'm going to import from scikit-learn. I'm going to use decomposition, and I'm going to import principal component analysis. I'm also going to import NumPy as NP. And then I want to set our PCA is going to be equal to principal component times n components. And I'm going to set that equal to 2. You can choose how many you want here. But essentially what I'm telling it to do is I want to boil down all the features to just 2 new features. That's what I'm telling it in this part of the algorithm. And then I'm going to create a model that's going to be equal to PCA.fit transformation. And I want to perform the transformation on our X. And then I'll make a data frame called PCA.df. And I'll just equal that to data frame. And then the data will be equal to the output of our model. And then the columns will be equal to PC1, PC2, PC1 and PC2. And then I can print out that data. So now we just created 2 new features for our data for each one of our observations. And right now it's really hard to tell what this means. However, we can fix that by using a loadings matrix to actually look into what each one of these components actually means or represents. So if I go to loadings, to principal component analysis, and then I use the component dot transform, multiply that by the square root of our explained variance. That gives us loadings. Then I can create a loadings matrix. And that's just going to be equal to our data frame, loadings, and then the columns, all equal to PCA df dot columns, and then the index will be equal to our df ready dot columns. And then we can look at this loading matrix. Oops, was this loadings? There we go. Okay, so now this tells us the weights that are put on each one of these features. So we can see how each one of our features affects our new features that we created. So I know as this is, it might not completely make sense. So I want to do a quick visual to show you what's going on back in Excel. So let me just take this first observation we have here. I'm going to put that into an Excel sheet. So that is our first observation. We have now here is our loadings matrix. Let me get this into Excel as well. And let me move that over. And then these are our new components for observation 1. So what is going on here is, let me transform this. What we're saying is for PC1, we do this, principal component 1 is going to be equal to this times our loadings, or times this number here. And then we're going to sum all those up. Okay, wait, so I just realized I entered the actual numbers. I didn't enter the standardized numbers, and that's what should be entered. And in addition, I also squared it by the variance, just so I just multiplied all these by the variance, so of the two columns. So it actually would be kind of tricky to extract all this information. But the essential idea is that you would multiply whatever the input values are by these loading values, and then you'd put them together, and that ultimately gives you what the outputs are for the two components. Now I'm not going to get into that just because I just realized how much more math that's going to take just to be able to extract all this. But just know that's the general idea for what loadings mean. Is loading is basically tying how much of the variance does sepal length make up for this principal component and so forth. And actually one thing, let me see if this holds true, but I think these numbers should add up to 100%. Let me try this out. Oh, no, not quite. Yeah, we're not going to be able to use these. Um, they're coefficients, not percentages, but that's how you interpret the loadings matrix. Is it's telling you what what columns make up what variance for the new features that we extracted. And so then what I can do is I can take this loading matrix that we have, and then I can go ahead and I can use an absolute value function, and then I can do find what the max is for each of the columns. And this tells me essentially that sepal length, petal width all fall on PC1, where sepal width falls on PC2. And I'll show you why that's useful and how we can interpret that in just a moment. But before I do that, let's get all of our data back together. I'm going to create a new data frame called PCA model output, and I'm going to merge this onto our KNN model that we had. And then I'm going to merge that with our PCA data frame. How am I going to merge these? Well, I want to use an inner join to make sure we don't lose any, that we're only matching data that both sides has. I want to join on the left index. And I'll also want to join on the right index. Okay, and that gives us all the data. We have our assigned clusters, species, our name, and even our principal components that we have over here. And now what I can do is I can I'm going to create a scatter plot in Seaborn to plot this data. And I want to use the data from our PCA model output that we just created. The X is going to equal PC1. The Y is going to equal PC2. And then the hue is going to equal our assigned cluster. And just for fun, I'll add in style for species. And lastly, I do not want to have a legend. Okay, and let me show the plot. Did we define this up here? Oh, output. Okay, and there you go. And this is what our dimension reduction algorithm has done, is it's taken all of these dimensions, squished them down in a way that shows the most amount of variance. And if you see, this view, having these two dimensions, is a very good job of spreading out all the data so we can see what is going on, or we can capture as much variance as possible. And this is where this loadings matrix comes in handy, is it helps us interpret what PCA1 and PCA2 is. For instance, since I know PCA1 is primarily that these columns have, that these weights have greater effect on PC1 than they do on PC2, on principal component 1 rather than principal component 2. What I'm going to do is I can say on our X label, I am going to add all this information into it. So, and then I can do the same thing for PC2 is going to be sepal width. Oops, fix that. Y label. So this is then how I can interpret these axes. For this axis represents sepal width, and then this axis represents sepal length, and petal width. Why this is so incredibly useful is, let's say that I was comparing a bunch of different firms with each other, and I was trying to figure out where they compete in a market. What I can do is I can take the attributes of those firms, run it through a cluster analysis and then a principal component analysis like this, and then I can display it on these two dimensions that I produce. And these two dimensions will represent a group of attributes. And then I can see how different firms are positioned relative to each other based on those attributes. So that is why being able to do dimension reduction is so valuable, and is probably one of the most used, used machine learning algorithms I use when doing analysis. Um, so that's great if you want to if you want to create new dimensions. However, that's not always as desirable to create new dimensions. Sometimes you just want to figure out which of these variables, or which of these features represents the most variance. Well, there's also another way to do that where I can let me go back up here. So I was looking at what were the maximum values, whether I was basically with this function or this script line of code saying, well, tell me if PCA1 or PCA2 is higher for these. Now what I'm going to do is I'm going to ask it which one of these has the highest for PC1 and which one has the highest for PC2. So I'm going to change the index from 1 to 0. And then if I do that, I can see that petal width has the greatest variance for PC1, and then sepal width has the greatest variance for PC2. And let me make a new graph with that. But this time, instead, what I'm going to do is I am going to just assign petal width to PC principal component 1, and then petal length, I'm sorry, sepal width to PC2. And if I run that, you notice that while this graph does better show the spread, this is still relatively captured in this graph. I can still see that this has the most amount of variance between these two variables. So if I don't want to melt all the variables into just one dimension, this is a great way to choose your top two variables. And this is kind of like, with this, going back to the example with the housing, is if we threw in the housing data into this variable would just turn into length. It would mush together both square feet and square meters. Where in this example, it just throws away square meters and keeps square feet. And if we look back up at our pair plot up here, what was that? That was petal width and sepal width. So we look at, where is it? Petal width and sepal width. We can see that out of all the graphs, it does really divide up. It takes up the most amount of space out of any of the graphs, which means it really does show the difference, the variance in data. And then you can also see that where petal width, going back down here, where overall petal width is the best indicator for variance because you look at this um you look at this graph up here, you can see that petal width separates the data, um is able to best separate the data. So does petal length, but not quite, and both petal width and petal length are highly correlated, but petal width does a better job. Sepal width does a terrible job. Um, Sepal length does an okay job. So really you can see like sepal, but sepal length is on a completely different axis as petal width. So I guess a hypothesis you can come to with this is just that petal length, and petal width, petals are the best differentiator of this flower data set. Um, but that's how all of this ties together. Lastly, I do want to show some more follow-up analysis you could perform using this. Um, let me get all of this back together in one line of code so we're not constantly redoing everything. I'll need I'll need to standardize the data that we'll have. Need to um, standardize the data, then we'll need to actually fit a model to it, and then we'll need to get our loadings matrix. And then I want to look at these. So then what I can do is I can go ahead and start dropping different columns if I'd like to. I can see, okay, sepal width, I know that has the most amount of variance out of all the columns, so I'll just keep that, and then I can go ahead and drop sepal width. So let me go ahead and drop sepal width from the data. I'll run that. Let's see that. Oh, everything was highly correlated. Sepal length. Next, I know that sepal length is the most different out of these. We drop sepal length. And then I can see that probably petal width would be the next one that I'd want to drop. So just play around with this. This takes a lot of intuition to really figure out how to do. And this is probably playing around with dimension reduction is one of the most complicated, um, models that you can do in machine learning, just because, as we saw with the regression analysis, if you can figure out how to do this and do it well, you can really dive into the explanatory reasons of why things happen, which is huge because let's say like if Facebook is able, for instance, with all the features they get and they are able to identify by using feature extraction and reducing dimensions to figure out which what mechanisms make you click on ads more or drive up their revenue, that is huge for them because they are then able to just turn up that variable as much as they want and to be able to try to increase the revenue as much as they can based off that. Um, let's also, just for fun, what if I add 3 components in here? Let's do PC3. I'm not going to drop these anymore. Let's first see how this all separates up. Oh, so even with 3 components, we still are getting the same kind of stick. Let's see, which one makes it? So petal width, sepal length, and sepal width are the top 3. Are the top 3 are the top 3 variables with the most variation from each other. So petal width. I guess what we're seeing here is petal width. Petal width and petal length are so highly correlated, they keep getting smushed together. Where there's enough difference between sepal width and sepal length that they're remaining separate. So play around with this. All for this assignment, really what we're trying to do is get a graph that looks like this for whatever data you have. I'm not really going to look at if you can interpret everything that the model is doing. Rather, all you need to know is how to get to um, this information, and just being able to have enough intuition to know what that means. However, if you do want to go above and beyond and actually really use this in the real world to do some super awesome stuff, then it is going to require a much greater understanding of what's going on with loadings and how the features can be selected. But that'll be all for this video. In the next video, we are going to be wrapping this together and actually graphing this analysis on a slide.